Hello everyone, I'm Farhat from ECEC section. In today's video, we're going to talk about development of quantum computers. Let's see the overview. In this video, we are going to talk about the introduction and history and data representation, operations on data, Shor's algorithm, conclusion and open questions. Introduction. Let's see what is a quantum computer. It is a machine that performs calculations based on the laws of quantum mechanics, which is the behavior of particles at subatomic level. I think I can safely say that nobody understands quantum mechanics. This line is told by Feynman. Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics in 1982. In 1985, David Deutsch developed the quantum Turing machine, showing that quantum circuits are universal. In 1994, Peter Shor came up with a quantum algorithm to factor very large numbers in polynomial time. In 1997, Love Grover developed a quantum search algorithm with O root n complexity. Let's see what is the data representation. Qubits. A bit of data is represented by a single atom that is in one of the two states denoted by 0 and 1. A single bit of this form is known as qubit. A physical implementation of a qubit could use the two energy levels of an atom, an excited state representing 1 and a ground state representing 0. Here is the state 0 diagram, which converts to state 1. Okay. Superposition. A single qubit can be forced into a superposition of two states denoted by the addition of state vectors. Psi is equal to alpha 1 of 0 plus alpha 2 of 1, where alpha to the power 1 and alpha to the power 2 are complex numbers and alpha 1 square plus alpha 2 whole square is equal to 1. A qubit in superposition is in both of the states 1 and 0 at the same time. Consider a 3-bit qubit register. An equally weighted superposition of all possible states would be denoted by this equation shown here. Data retrieval. In general, an n-qubit register can represent the numbers 0 through 2 to the power n minus 1 simultaneously. If we attempt to retrieve the values represented within the superposition randomly collapses to represent just one of the original values. In our equation, psi is equal to alpha 1 of 0 plus alpha 2 of 1. Alpha 1 represents the probability of the superposition collapsing to 0. The alphas are called probability amplitudes. In a balanced superposition, alpha is equal to 1 by root 2, where n is the number of qubits. Relationships among the data. Entanglement. Entanglement is the ability of the quantum systems to exhibit correlations between states within a superposition. Let's imagine two qubits, each in the state of 0 plus 1, a superposition of 0 and 1. We can entangle the two qubits such that the measurement of one qubit is always correlated to the measurement of the other qubit. Let's see what are the operations on data. Operations of qubits. Reversible logic. Due to the nature of quantum physics, the destruction of information in a gate will cause heat to be evolved, which can destroy the superposition of qubits. Example, let's take AND gate. In inputs, A is 0 and B is 0, we get C is also 0. When A is 0 and B is 1, the output is 0. When A is 1 and B is 0, the output is 0. When A and B both are 1 and 1, the output C is 1. In these three cases, information is being destroyed. This gate cannot be used. So we must use quantum gates. Let's see what are quantum gates. Quantum gates are similar to classical gates, but do not have a degenerate output, that is, their original input state can be derived from their output state uniquely. They must be reversible. This means that deterministic computation can be performed on a quantum computer only if it is reversible. Luckily, it has been shown that any deterministic computation can be made reversible by Charles Bennett in 1973. Hadamard. Simplest gate involves one qubit and is called Hadamard gate, also known as square root of NOT gate, used to put qubits in superposition. Note, two Hadamard gates used in succession cannot be used as NOT gate. Controlled NOT. A gate which operates on two qubits is called a controlled NOT CN gate. If the bit on the control line is 1, invert the bit on the target line. As shown in the figure here, let's give the inputs and outputs and get outputs. When A is 0, B is 0, then A dash is also 0 and B dash is also 0. When A is 0 and B is 1, we get A dash is also 1, B dash is also 1. When A is 1, B is 0, we get A dash is 1 and B dash is 0. When both A and B are 1, we get A dash 0 and B dash 1. Note, the CN gate has similar behavior to the JOR gate with some extra information to make it reversible. Example operation. Let's see what happens when we multiply by 2. We can build a reversible logic circuit to calculate multiplication by 2 using CN gates arranged in the following manner. Quantum gates, CCN, controlled NOT gates. A gate which operates on 3 qubits is called controlled NOT, CCN gate. If the bits on both of the control lines is 1, then the target bit is inverted. Here we can see inputs and outputs. A universal quantum computer. The CCN gate has been shown to be a universal reversible logic gate, as it can be used as NAND gate. Here are the inputs and outputs. When our target input is 1, our target output is a result of NAND of B and C. Let's see what is Shor's algorithm. Shor's algorithm shows that a quantum computer is capable of factoring very large numbers in polynomial time. The algorithm is dependent on modular arithmetic, quantum parallelism, quantum Fourier transform. Shor's algorithm, periodicity. An important result from the number theory, f of a is equal to x to the power a mod n, is a periodic function. Let's choose n is equal to 15 and x is equal to 7, and we get the following. Shor's algorithm. Factor an odd integer n. For example, let's choose a number 15. Choose an integer q such that n square is less than q is less than 2n square. Let's pick 256. Choose a random integer x such that the GCD of x, n is equal to 1. Let's take 7. Create 2 quantum registers. These registers must also be entangled so that the collapse of the input register corresponds to the collapse of the output register. Input register. It must contain enough qubits to represent numbers as large as q minus 1. So in this case, we have taken 256 to up to 255. So we need 8 qubits. Output register. It must contain enough qubits to represent numbers as large as n minus 1. So up to 14, we need 4 qubits. Let's prepare the data. Load the input register with an equally weighted superposition of all integers from 0 to q minus 1. Load the output register with all zeros. The total state of the system at this point will be as shown. The comma here denotes that the registers are entangled. Modular arithmetic. Apply the transformation x to the power a of mod n to each number in the input register, storing the result of each computation in the output register. We are using decimal numbers here only for simplicity. And here are the inputs and outputs. Superposition collapse. Now, take a measurement on the output register. This will collapse the superposition to represent just one of the results of the transformation. Let's call this value C. Output register will collapse to represent one of the following, that is 1, 4, 7 or 13. For example, let's choose 1. Entanglement. Now it gets interesting. Since the two registers are entangled, measuring the output register will have the effect of partially collapsing the input register into an equal superposition of each state between 0 and q minus 1 that yielded C, the value of collapsed output register. Since the output register collapsed to 1, the input register will partially collapse to as shown. The probabilities in this case are 1 by root 64. Since our register is now in an equal superposition of 64 values. We now apply the quantum Fourier transform on the partially collapsed input register. The Fourier transform has the effect of taking a state A and transforming it into a state given by, as shown. In this, A is a set of values that 7 to the power A mod 15 yielded 1. In our case, A is equal to 0, 4, 8, so on up till 252. So, the final state of the input register after the QFT is as shown. The QFT will essentially peak probability amplitudes at integer multiples of q by 4 in our case, like 256 by 4 or 64, 0, 64, 128, 192. So we no longer have an equal superposition of the states. The probability of amplitudes of states are now higher than the other states in our register. It will collapse with a high probability to one of those multiples of 64. Let's call this as P. With our knowledge of Q and P, there are methods of calculating the period. Now that we have the period, the factors of n can be determined by taking the greatest common divisor of n with respect to x to the power p by 2 plus 1 and x to the power p by 2 minus 1. The idea here is that this computation will be done on a classical computer. Let's compute GCD of 7 to the power 4 by 2 plus 1, 15 is equal to 5. And GCD of 7 to the power 4 by 2 minus 1, 15 is equal to 3. We have successfully factored 15. Problems. The QFT comes up short and reveals the wrong period. This probability is actually dependent on your choice of Q. The larger the Q, the higher the probability of finding the correct probability. The period of the series ends up being odd. If either of these cases occur, we have to go back to the beginning and pick a new X value. Let's conclude. In 2001, a 7-qubit machine was built and programmed to run Shor's algorithm to successfully factor 15. What algorithms will be discovered next? Can quantum computers solve NP-complete problems in polynomial time? Let's answer these questions. Thank you so much.